Hello everyone. Today we're going to look at how to evaluate limits algebraically. So in order to start us off, we're going to take a look at this function, f of x is equal to x squared plus x over x squared plus 4x plus 3. And what we're going to do is we're going to fill out this chart. We're going to find the function value if we were to take that number and just plug it in directly. And then we're going to use the graph of the function in order to evaluate for its limit. So first we're going to start with f of negative 3. If we plug it in, we get negative 3 squared, which is 9, plus negative 3, so minus 3, over negative 3 squared, which is 9, plus 4 times negative 3, which is minus 12, plus 3. And what I end up getting here is 6 over 0. Which would be undefined. Now if I look at the graph, however, when I go to x is negative 3, I see that we have a vertical asymptote, which is why we got that value as undefined. Therefore, the limit does not exist, since it is a general limit. If it was a one-sided limit, then we'll look at the left side or the right side. For f of negative 1, again, we're going to just go ahead and plug it in. When we plug it in, we get 1 minus 1 over 1 minus 4 plus 3. And I end up getting here 0 over 0, which is also undefined since we can never have 0 in the denominator. However, when I look at the graph and I go to x is negative 1, I see that we do have a limit value. And the limit value would be negative 1 over 2. Even though it is a whole, but the left and the right side do equal. Now when we're finding f of 0, when I plug it in, we get 0 plus 0, which is 0 in the numerator, over 0 plus 0 plus 3. And 0 over 3 would be 0. So this would be my function value. And if I look at the graph, the limit value is also 0. So if a function is defined and continuous, because for a is equal to negative 3 and for when a is equal to negative 1, we have here points of discontinuity. We have the asymptote and then we have that point discontinuity, which is the whole. But if it is defined and continuous, such as when a is 0, we can determine the limit analytically, meaning algebraically, by just plugging in. Which leads me to our first method of evaluating limits, which is the substitution method. The substitution method is simply when you take that value that x is approaching and plug it in directly into the equation. So for example, for the limit as x is approaching 0, if I were to plug it in, I would get negative 1 in the numerator over 3. And this is my limit value. For the limit as theta is approaching 2 pi over 3, I'm going to go ahead and plug it in. So we get cosine of 2 pi over 3 all over 2 pi over 3. Now when you're finding this limit value, you do need to know your unit circle. But just so you can see, I have the unit circle here. If I go to 2 pi over 3, the cosine is negative 1/2. So we have negative 1/2 in the numerator all over 2 pi over 3. Since here we are dividing fractions, we're going to multiply by the reciprocal of the denominator, which is 3 over 2 pi. Now we just multiply across, and we get that our limit is equal to negative 3 over 4 pi. For this last one, we see that the limit is approaching 2 from the left. Now, if you can just plug in the number, it does not matter whether it's coming from the left or the right. You can go ahead and just plug it in and see if you get an answer. So if we just plug it in, we would get the square root of 2 plus 2, which is 4, minus 1 over 2 plus 1. The square root of square root of 4 is 2, minus 1 over 3. So this gives me a positive 1 over 3. Now the substitution method should always be the first one that you try because it's the easiest one, and as long as you can plug it in and you get an answer, that would be your limit value. But if the substitution does not work, there are other methods. Before we go ahead and do that, let's go ahead and just continue practicing the substitution method. So for the limit as x is approaching 2 of 5x plus 2 over 2x plus 3, we're just going to go ahead and plug in that 2. So we get 5 times 2 plus 2 over 2 times 2 plus 3. 5 times 2 is 10, plus 2 is 12, over 2 times 2 is 4, plus 3 is 7. So we get 12 over 7. For the limit as theta is approaching pi over 2, we're just going to go ahead and plug it into sine of 2 times pi over 2. Now all of this is the angle, so we can cancel out these 2's. This then leaves me with the sine of pi. And if you look at your unit circle, which I'll pull it up just in case, if I go to pi, the sine of pi, which is the y value, is 0. For this last one, we're going to go ahead and plug in x is equal to 3. So we have 1/2 times 3 squared minus 2 times 3 plus 3. 3 squared is 9, divided by 2 is 9 over 2, minus 6 plus 3. This will then give us 9 over 2 minus 3. And then here we're going to need a common denominator. So I'm going to go ahead and put this over 1. The common denominator is 2, so I'm going to multiply this by 2 and this by 2. We get 9 over 2 minus 6 over 2, which is equal to 3 over 2. Now, if the substitution does not work, so for example with these two here, we're going to go ahead and just try plugging in the numbers and see what happens. Okay, so if I were to plug in x is approaching negative 3 into x squared plus 2x minus 3 over x squared plus 5x plus 6, we would get negative 3 squared, which is 9, plus 2 times negative 3, which is negative 6, minus 3, over negative 3 squared, 9, plus 5 times negative 3, which is negative 15, plus 6. This will end up giving me 0 over 0. And anything over 0 would technically does not exist because this value is undefined. Now let's try it over here. If I were to plug in negative 2, negative 2 squared is 4, plus 2 times negative 2 is minus 4, minus 3, over negative 2 squared, 4, plus 5 times negative 2, which is negative 10, plus 6. And this gives me negative 3 over 0. Again, it's over 0, so this does not exist. However, just because we got does not exist using the substitution method does not necessarily mean that the limit does not exist. Now what we have there was a rational function. So if we look at the graph, okay, this is the graph of that rational function that we were just testing. If we look at the limit as x is approaching negative 3, which we got over here as 0 over 0. If we look here at negative 3, we can see that we do have a limit value. And although you can't see it, each one of these lines here is 2. So that limit value would equal to 4. And that's because we have a hole. Now for when x is approaching negative 2, when we plugged it in, we had gotten undefined as well. But if we look at the graph, and if we were to find both the left and the right side limits, we can actually use the graph to find those limits. Now at x is equal to negative 2, we have a vertical asymptote. So if I were to plug in, or rather if I were to find the limit as x is approaching negative 2 from the left, I see that it is going up, and therefore this limit would equal to infinity. If I were looking at the limit as x is approaching negative 2 from the right, I see it's going down, so this limit is negative infinity. Now remember, these are one-sided limits, so my answer could very well be infinity or negative infinity. However, if this was a general limit, meaning just the limit as x is approaching negative 2, then that limit would still does not exist because of that vertical asymptote. Now, how do we get these limit values if we don't have a graph? That leads us to the second method, which is the factoring method. And this works when we have rational functions. Remember that rational functions is when you have a fraction. So I put here some steps for you here to follow. The first step would be to factor the numerator and the denominator completely. So we're going to go ahead and look at this numerator. X squared plus 2x minus 3 can be factored to be x plus 3, x minus 1. And then x squared plus 5x plus 6 can be factored to be x plus 3, x plus 2. So then what happens here is that these x plus 3's cancel, and I'm left with the rational function x minus 1 over x plus 2. Now if I wanted to plug in that negative 3, I can. If I were to plug in negative 3, I would get negative 3 minus 1, which is negative 4, over negative 3 plus 2, which is negative 1, which gives me that limit value that I got when I used the graph of 4. Now again, this is the same function, so I'm going to use my simplified version, x minus 1 over x plus 2. Notice that this is the limit as x is approaching negative 2 from the left. If you have a one-sided limit, but I can't plug in the number because I still get 0 in the denominator, then what you do is you pick a number slightly to the left of negative 2 since it's coming from the left. And a number that is slightly left of negative 2 is x equals negative 2.1. And I'm going to take this number and I'm going to plug it into my function. Now, I don't necessarily care what the value is. I already know that because at x is equal to negative 2, since the denominator is 0, that's where I have a vertical asymptote. So I know that one of my answers is going to be infinity, some type of infinity, whether it's positive or negative. So all I really care about is what the sign is. If I plug in negative 2.1 into the numerator, I get negative 2.1 minus 1, which is a negative number. And if I plug it into the denominator, I get negative 2.1 plus 2, which is still a negative number. A negative divided by a negative is a positive, and because this is an asymptote, I know that my limit would be infinity. And again, we can verify this using the graph that or finding the limits using the graph. See here we have that limit as x is approaching negative 3, which was 4, and then here we have that limit as x is approaching negative 2 from the left, which is infinity. So let's go ahead and apply and try it out with these particular limits. So the first one, we have the limit as x is approaching 2 of x squared minus 6x plus 8 over x minus 2. So I'm going to go ahead and factor that numerator, which can be factored to be x minus 2, x minus 4, over x minus 2. My x minus 2's cancel out. So that's your point of using the factoring method, is to get rid of that problematic factor that's in the denominator. Now my function is simplified to be just x minus 4. So what we're really finding now is the limit as x is approaching 2 of x minus 4. I can plug in the 2, and I would get 2 minus 4, which is negative 2. For the following one, we're going to go ahead and try to factor this as well. We're finding the limit as x is approaching 4 from the left. X squared minus 1 is a difference of squares, so I can factor that to be x plus 1, x minus 1. And the denominator, x squared minus 3x minus 4, can be factored to be x minus 4, x plus 1. The x plus 1's would cancel out. And what I end up with here is the limit as x is approaching 4 from the left of x minus 1 over x minus 4. Now this is what happens. If I were to try to plug in the 4, I still get 0 in the denominator. This means that I have a vertical asymptote at x is equal to 4. And what this indicates is that my function is going to approach some kind of infinity. Since I'm trying to find for when x is approaching 4 from the left, I'm going to plug in a number slightly to the left of 4 so that I can note the sign and then determine which infinity it's approaching. So here we go. So I'm going to go ahead and plug in x is equal to 3.9. If I plug in 3.9 in the numerator, I get 3.9 minus 1, which is positive. And in the denominator, 3.9 minus 4 is negative. A positive divided by a negative is negative. And since this is an asymptote, it's approaching infinity. Therefore, my limit as x is approaching 4 from the left of x squared minus 1 over x squared minus 3x minus 4 is negative infinity. We're going to try the same process for the limit as x is approaching negative 3 from the right of x squared minus x minus 2 over x squared plus 2x minus 3. So I'm going to go ahead and factor this numerator. X squared minus 3x minus 2 can be factored to be x minus 2, x plus 1, over x squared plus 2x minus 3 can be factored to be x plus 3, x minus 1. Nothing cancels here. Therefore, if I were to try to plug in that negative 3 right here, I would end up getting 0 in the denominator, meaning that x is equal to negative 3 is a vertical asymptote. So we have to do the same thing we did for the previous problem. We're going to plug in a number that is slightly to the right of negative 3. So what I'm going to do is I am going to plug in x is equal to negative 2.9. And I'm going to take note of the signs for the numerators and the denominators so that I know which infinity my function is approaching. If I plug in negative 2.9 into this first factor, we would get negative 2.9 minus 2, which is a negative number. If I were to plug in negative 2.9 into x plus 1, I would get another negative number. In the denominator, if I were to plug in negative 2.9 into x plus 3, I'd get a positive number. And if I were to plug it into x minus 1, I would get a negative number. Now overall, in the numerator, a negative times a negative is a positive, and in the denominator, a positive times a negative is negative. And once more, because I have a positive divided by a negative, that means that my answer is negative infinity. Now in these cases here, we see that we have rational functions, but we won't be able to factor it. And that's because we have that square root. These are radical rational function combos, as I like to call it. Okay, substitution sometimes won't work. See, if I were to plug in the 16, that denominator would give me 0. So instead, what I'm going to do is I am going to multiply the conjugate of the radical expression to both the numerator and the denominator. Keep in mind that the conjugate is when you switch the middle sign of that term, of the binomial, excuse me. So I'm going to go ahead and multiply by the conjugate, which is the square root of x plus 4. See, I just changed the sign of the middle term. And whatever I do to the numerator, I must do to the denominator. Now, wherever you have your conjugates, you're going to actually multiply that out. Okay, so for example, here, the square root of x minus 4 times the square root of x plus 4, I'm going to FOIL. Now, if you FOIL correctly, your middle terms always cancel out for conjugates. I'm going to work it all out now so you can see. The square root of x times the square root of x is x. The square root of x times 4 is positive 4 square root of x. Then negative 4 times the square root of x is negative 4 square root of x. And negative 4 times 4 is negative 16. See how these middle terms end up canceling out. Now in the denominator, or in whatever case, wherever it is, when you're multiplying the terms that are not conjugates, don't actually multiply it out. It's going to make things much more complicated. But instead, you just write it out as if you were. So x minus 16 times the square root of x plus 4. Notice that I didn't actually multiply it, I just write it right next to each other. So now what ends up happening is when you simplify your function, we get x minus 16 in the numerator over x minus 16 times the square root of x plus 4. That factor, x minus 16, cancels, which is the factor that was giving me an issue because when I plug in 16, I would get 0 in the denominator. So now I can simplify this limit. What I'm looking for now is the limit as x is approaching 16 of 1 over the square root of x plus 4. And now we can use the substitution method. I can go ahead and take the 16 and plug it in. If I plug it in, I get 1 over the square root of 16 is 4, plus 4, 8. So my answer here is 1 over 8. For this next one, I'm going to go ahead and multiply by the conjugate of the radical expression. So I'm going to multiply by the square root of 2x plus 1 plus 3. Now remember, whatever you do to the numerator, you must do to the denominator. For the numerator here, the x minus 4 times the square root of 2x plus 1 plus 3, I'm not going to actually multiply them out because these are not conjugates. I'm just going to write them next to each other. So x minus 4 times the square root of 2x plus 1 plus 3 all over. And now remember, because these are conjugates, those middle terms cancel out. So if you wanted to take a shortcut, you can multiply the first terms and then multiply the last terms. The square root of 2x plus 1 times itself is just 2x plus 1. And see, if I were to FOIL, I would have a positive 3 square root of 2x plus 1 with a negative 3 square root of 2x plus 1, which cancels. And so then all I would have to multiply left is the negative 3 times 3, which is minus 9. So now let's continue to work this out here. So we have in the numerator this x minus 4 times the square root of 2x plus 1 plus 3. And in the denominator, I'm going to do this here in a separate color, 2x plus 1 minus 9 is 2x minus 8, which if I wanted to, I can factor a 2 from each term, which is 2, and then times x minus 4. So that's actually my new denominator, 2 over x minus 4. And what happens here is that those x minus 4's cancel. That's the whole point of using the conjugate method. You want that problematic factor to cancel out. So now I'm going to rewrite my limit. So the limit as x is approaching 4, and all I have left in the numerator is the square root of 2x plus 1 plus 3, and everything is over 2. And now I can plug in the 4. 2 times 4 is 8, plus 1 is 9. The square root of 9 is 3. And then I have this other plus 3 over 2, which gives me 6 over 2, and 6 divided by 2 is 3. Now we're going to look at how to apply all three of these methods. So we're going to look at various examples. For this first one, I don't have a rational function. It is a radical, but it's not a rational. So I can just go ahead and try the substitution method. If I were to plug in the limit as x is approaching 0, what I would get is square root of 9 minus 4 times 0 is 0 plus 0 cubed is 0. So I just get the square root of 9, which is equal to 3. For b, I have a rational function. See, if I were to plug in this negative 1, in the denominator I would end up with negative 1 squared, which is a positive 1 minus 1, which gives me 0. So therefore, because I would get a 0 in the denominator, I have to find another method, meaning that I'm going to use the factoring method. So I'm going to go ahead and factor this numerator. X squared plus 6x plus 5 is x plus 5 times x plus 1. X squared minus 1 is a difference of squares, so x plus 1 times x minus 1. The x plus 1's cancel, and so now I can rewrite my limit with my simplified rational function, which is the limit as x is approaching negative 1 of x plus 5 over x minus 1. And now I can plug it in. If I plug in negative 1, in the numerator I would get negative 1 plus 5, which is 4, over negative 1 minus 1, which is negative 2, and 4 divided by negative 2 is negative 2. Moving on to this next one, I noticed that we have a rational function with a square root. If I were to plug in the 4, I would get 2 minus the square root of 4 in the denominator, which ends up giving me 0. Therefore, I'm going to have to try using the conjugate method. So I'm going to multiply by 2 plus the square root of x to both the numerator and the denominator. Remember, in the numerator, these are not conjugates, so I'm just going to go ahead and write it next to each other. 4 minus x times 2 plus the square root of x over, now these are my conjugates. I'm going to do my shortcut where I'm only going to multiply the first and the last terms. 2 times 2 is 4, minus the square root of x times the square root of x is x. And as you can see, that 4 minus x cancels out. So now I'm looking for the limit as x is approaching 4 of 2 plus the square root of x. So when I plug in the 4, I get 2 plus the square root of 4, which is 2. And 2 plus 2 is 4. Now for this one, I notice that I have fractions subtracting in the numerator. So I'm going to focus with that part first. I want to simplify this to be one fraction, so then I could work out the rest of it. Now 1 over 3 minus 1 over x, I'm going to need a common denominator. And if you're ever unsure of your common denominators, you can just multiply them together. So for 1 over 3, my common denominator here is 3x. So I need to multiply 1 over 3 by x to both the numerator and the denominator. And for 1 over x, I'm going to need to multiply by 3 to both the numerator and the denominator, giving me x minus 3, that's this part here, over the denominator, which is 3x. And everything is over x minus 3. Now you have a fraction divided by x minus 3. What you can do is multiply by the reciprocal of x minus 3. Remember that if you have something that's not a fraction, you can always put it over 1. And then you can copy, change, flip, which is the same as multiplying the reciprocal. So I have my numerator, x minus 3 over 3x, and I'm going to multiply by the reciprocal of the denominator, which is 1 over x minus 3. These x minus 3's cancel, and I'm left with 1 over 3x. Now I can rewrite my limit, the limit as x is approaching 3 of 1 over 3x, and I can plug in the 3 now. 1 over 3 times 3 is 9. And this would be my limit value. Now we're going to move on to look at some various properties of limits. If we had the limit as x is approaching a of f of x, we're going to say that that value is L. And if we have the limit as x is approaching a of g of x, we're going to call that value m. And c is some constant. If I were to look at all of these limit statements, so see here, the first one we have the limit as x is approaching a of f of x plus g of x. What that means is that I can take the limit value of as x is approaching a of f of x and add it to the limit value as x is approaching a of g of x. This means that if I'm using these letters that I assigned here at the beginning, that we would get L plus m. And the same would apply for subtraction. So the limit as x is approaching a of f of x minus g of x would be L minus m. And it's the same concept with all of our properties. So if we're dividing, we would do L over m. If you have a constant that is being multiplied to your function, you can move the constant to the outside and multiply it later. So if I knew that the limit as x is approaching a of f of x is L, then I would multiply that constant to L after the fact. If you have your limit value is raised to an exponent, you can find that limit and then raise it to that exponent. So this would be L raised to the exponent of p. And if you have the limit as x is approaching a of a constant, okay, anytime you have the limit approaching a value of some constant, the answer is always the constant. Doesn't matter where it's approaching. Because think about it, if you have a constant, right, let's say you have a graph A constant means that you have a horizontal line. So it doesn't matter what x is approaching, the y value will always be the same. So now let's go ahead and apply these properties of limits. We have this graph of f of x and the graph of g of x. If I was looking for the limit as x is approaching 2 from the right of f of x plus g of x, I'm going to look at the limit as x is approaching 2 from the right for f of x, which is negative 2, plus the limit as x is approaching 2 from the right of g of x. Here's g of x, this is 2, the limit from the right is 6, and negative 2 plus 6 is 4. Easy peasy. Next, we have the limit as x is approaching negative 3 of 2 f of x minus 3 g of x. So we have 2. Remember the constant we can multiply after we find the limit. I'm going to find the limit as x is approaching negative 3 of f of x, which is negative 2, minus 3. And now I find the limit as x is approaching negative 3 of g of x, which is right here, so 1. So this gives me negative 4 minus 3, which is equal to negative 7. For the limit as x is approaching negative 6, we have negative 2 f of x. So I'm going to come over here, go to x is negative 6, which is 1, over g of x, the limit as x is approaching negative 6 of g of x, which is 4. Remember that the limit you have to follow the function, not these defined circles. Okay, so the actual limit value is the 4. Negative 2 times 1 is negative 2 over 4 is negative 1 over 2 simplified. Over here, we have the limit as x is approaching 4 of 2 f of x times g of x. So I have 2. I'm going to find the limit as x is approaching 4 for f of x, which is negative 3, times the limit as x is approaching 4 of g of x, which is 4. 2 times negative 3 is negative 6, times 4 is negative 24. Over here, we have the limit as x is approaching negative 2 of f of x squared. So I'm going to look at the limit as x is approaching negative 2 for f of x, which is negative 5, and then I'll apply the exponent after I find that limit, which is positive 25. And finally, for this last one here, we have the limit as x is approaching 2 from the right of the square root of 2. And now I'm going to find that limit value for g of x. So I go to g of x, 2 from the right, so that's the 6. So this gives me 2 times 6, which is the square root of 12. And if you can ever simplify radicals, it's always good to do so, because in multiple choice questions for the AP exam, typically the answers are simplified. 12 is 4 times 3, and then 4 is 2 times 2. So here we have a pair, and this 3 is all by itself. So our radical will be 2 times the square root of 3. And that's finding limits algebraically.